If you take a coil of wire and put a magnet through it, what you'll find is that there's a current that is produced depending on how you move the magnet. So in this case, if we look at this magnet, it's going in the up direction, and the coil is going to have a current flowing in the clockwise direction we look down on it. And if I move the magnet down, the current is going to reverse direction, and it's going to be going in the counterclockwise direction as I look down on the coil. But if I don't make any movement with a magnet, there is no current. So there is a magnetic field around this wire, but it's not changing, it's constant, and so there's no current. Only when there's motion is there a current. This is no motion. So this was something that was observed by Faraday, and he came up with a relationship to understand how these two effects work. To understand Faraday's law, we have to go back to this idea of flux. Now, remember that we had electric flux, and we had this relationship. Electric flux is equal to the integral of the electric field dot differential area, and that was equal to Q enclosed over epsilon naught. Well, it turns out that for magnetic flux, we use the same type of definition, except in this case, we're going to have some magnetic field dot differential area, and it turns out that this equation is not so useful because it says that it's zero. And the reason why it's zero is if I take a magnet, I have south end, north end, and I have these magnetic lines, then no matter what shape I put around this magnet, the amount of flux lines going into or out of the shape is going to be the same amount of flux lines coming in. So there is no value other than zero that I can come up with to get to encompass all these lines. They circle in on themselves. But what Faraday noticed was that there was a relationship between the flux and the induced potential. Now, this relationship is negative times the number of loops d phi dt, and this phi is a function of t, and this is not the electric field. But an induced potential. So we take the very same definitions that we did for the electric field flux, and we use that for the magnetic field flux. So if we have a surface, in this case it's square, then the area vector is just perpendicular to that surface, and the magnetic field, the perpendicular part, is what we're concerned with. Anything that's parallel, there's no contribution. And only the perpendicular part contributes. So I'm going to have this this angle here, theta, and it's the cosine that I'm interested in. So if I want to find the value, and remember that flux is a scalar, then that's going to be equal to the magnitude of the magnetic field times the area times the cosine of theta. Very similar to what we had for the electric field, which was the electric field times the area times cosine of theta. And so Lenz's law basically says that the change in flux in the area surrounded by a loop of wire produces an induced potential related to the number of loops and the rate of change in flux. So this is a very important property that we have with magnetic fields, because now we're connecting a magnetic field to an electrical current that's induced. Now this negative sign in front of the N is going to be our next topic, Lenz's law.